Hello and welcome to lecture 15 of the course Computational Complexity. So in the last lecture we saw space bounded complexity classes like D space Fn, N space Fn, L, NL and so on. In this lecture we will see a specific a notion of completeness much like NP completeness called NL completeness, right? So even though the definition is going to be similar, the way these NL completeness behaves or the way the space bounded completeness behaves is a bit different. So the details we will see maybe in the next few lectures, but in this lecture we will define and see some basics, right? So to have a notion of completeness, we should have a notion, a reduction, appropriate reduction with us. And we cannot use, so when we reduce, let's say when you reduce a language A to a language B, and we are talking about, we are trying to compare like which class these are in, etc. The resources available for the reduction must be strictly lesser than the classes. So suppose we are doing NL completeness, so we will be dealing with languages or problems in NL. Okay, as we already saw in the previous lecture, NL is contained in P. So if we allow polynomial time reductions, then we could take a language and decide it in the polynomial time, because all these languages are in NL. So we need a more limited notion of reduction, which is not polynomial time reduction. And since we are studying space bounded complexity classes, we may as well use a space bounded reduction as well. So the reduction that we will use is log space reduction. So what does it mean? So A is reducible to B in log space, denoted by A less than or equal to B with a subscript L, okay, as against a subscript of P. In other words, A reduces to B in log space if there is a deterministic logarithmic space machine M given X or given W, it computes f of W, it computes a function f such that W is in A if and only if f of W is in B. So everything is very similar to polynomial time reductions. The only difference here is that this is the reduction, this is the difference. In polynomial time reductions, the machine which computed was restricted to polynomial time. Here the machine that is computing the reduction is restricted to deterministic log space. Okay, and this is W is in A if and only if f of W is in B is exactly like what we had in polynomial time reductions, or even in the theory of computation course mapping reductions, right? Okay, so now let's try to see whether this notion of reduction makes sense. So we had this neat thing in polynomial time reductions when A is in reducible to B in polynomial time and B is itself in polynomial time, then we could combine the reduction with the decider for B to infer that A is also in polynomial time, right? So can we do the same thing? Suppose A is reducible to B in logarithmic space, then if we have a decider for B, can we get a decider for A, right? So let's try to understand. Suppose A reducible to B in logarithmic space using a function f, right? Now given, let's say W is an instance of A, suppose length of W is n, right? What is the upper bound on the length of f of W? Okay. So how much space does this reduction take? The reduction takes order log n space, right? Because it's a logarithmic bounded reduction. How much time can it take? It can take a lot of time because, as we saw in the previous lecture, D space of Fn, right? Just to show the previous lecture notes, D space of Fn is contained in D time of 2 power order Fn, right? So anything that is possible in D space of Fn requires d time of 2 power order fn, because there could be that many configurations, 2 power order fn configurations, right? So here the number of configurations for this machine could be 2 power order log n, which is polynomial. So it could take up to polynomial time to compute the reduction. So in polynomial time, f of w is written down in polynomial time. So recall a log space bounded machine, we are only charging for the work tape. And if f of w is being computed, this computation, the result of this computation will be written down in the output tape. So the space usage in the output tape is not going to be accounted for. So f of w could potentially, every time step you could be writing one symbol over there. So this could be as bad as length of f of w could be as bad as, or as long as n power constant or polynomial space, right? And okay, so now a reduced to b. Now the instance of the length of the instance of reduced instance is polynomial space. Okay. Now the key question again, like we said over here, a reducible to b in polynomial time, b in polynomial time implies a in polynomial time. So can we say the same thing for log space reductions? A reduced to b in log space. Suppose b itself is in log space, is a also in log space? Right. So let us try to see, let's try to set up the same kind of framework, how we decided, how we saw that a reducible to b, how we saw it in polynomial time. Can we do the same for polynomial logarithmic space? So let R be the reduction machine. R be the reduction machine that takes the instance of a as input. Okay, so R is a reduction machine. So this takes a as a instance as input. It computes some work and it writes a instance of b as output. Okay, instance of b. Okay, and let m be the decider for b. Right? So m takes the whatever the instance of b that is given by R, and then it also has a work tape. So the m is shown as blue, R is shown as black, right? And then it decides accept or reject. So now if we combine the reduction machine, okay, and sorry, if we combine the reduction machine and the decider for b as one machine, right, this, the input tape of R will be the sole input tape, right, for the combined machine. This will be the sole input, and the work tape for R and the work tape for M, and even the output tape for R, which is the input tape for M, will have, all of this will together form the work tape for this combined R and M machine. Because as far as the, if you see the two machines together, this work tape, these two are work tapes which are read write, and this output for R and input for M is being written to by R and read by M. So this is actually effectively a read write machine once you combine this, right? So the work tape contains all of these three things, and as we already saw, suppose the A instance is of length n, right? So suppose we already saw that if length of w is n, then the length of f of w could be polynomial in the length of w. So that means the space usage just by the length of the b instance, that itself will be polynomial. What we are shooting for was the logarithmic in n. So this itself is polynomial. So this does not work. Right? So again, I have written down this in detail. If we try to make it decider for A by just combining R and M, the space used by the output tape of R, which is the input tape for M, will be polynomial in N. It will be polynomial in N because it comes from this, again, like we saw in the previous lecture. So the combined machine, so this is not a log space decider because it is using more space than, it is using polynomial space. Log space means we can only use O log n space. Okay. However, this question that we asked, if A reduces to B in logarithmic space and B is in logarithmic space itself, can A also be decided in logarithmic space? This question is still answered yes. This simply that this approach was wrong. Okay, so let us, what is the correct approach? Okay, so this approach was wrong where we tried to merge or combine R and A together, R and M together. This approach didn't work. So instead, we have to take a different approach because we cannot afford. So what happened here? What happened here is that we had to write the instance of B entirely, and this is something we cannot afford. So we will now try to do something where we do not have to write this down. Okay. So what we will do, let's say we want to decide A. Okay, so we start, so this is where we are. We have W, which is an A instance. A instance means we have to decide whether W is in A or not, right? So now we start the decider for B. Okay, so this may seem strange because decider of B needs the input of B, right? Okay, we just start it. Now let's say, okay, so the A instance is in my notes I have written it X. Okay, so not W. So we have X, which is the A instance, and we start the decider for B without any fx. F of X is not there. But at some point the decider for B will start looking at the input, which is the instance of B, which is F of X. So let us say when it wants a symbol, let us say it first looks at the first bit of F of X or first symbol of F of X. When that happens, then we remember that it needs the first symbol of F of X, and then we start running the reduction machine. Okay, we start running R, and once R outputs the first symbol, then we can continue running M. Okay, so in general, let us say M requires the jth symbol of F of X. So M needs some input, right? So this is let's say this is M input for M, input tape for M. Right, so it may not require each one of them in sequence. So maybe let's say it requires the 15th symbol. So then we start running R, the reduction machine, till, so we ignore everything like first bit, second bit, so on, till it writes the 15th symbol. Once it writes the 15th symbol, we just remember the 15th symbol, and M continues the computation. So now M is purely running, what is taken by M from R is only the 15th symbol, whatever it required for now. So like that, whenever it requires a certain symbol, let's say next it requires 20th this thing. So again now R is started from scratch till it computes the 20th symbol. Now again let's say it requires 7th symbol, so again R is started from scratch till it computes the 7th symbol. Again let's say 15th symbol is required by M, again R is started from scratch and again computed 15th symbol, even though it was already computed. Remember, M cannot afford to remember the entire F of X because just remembering the entire F of X requires polynomial space, and this is something we do not have. All that we have is logarithmic space. So every time we require a certain symbol of F of X, R recomputes it right from the beginning, or R computes it or recomputes it, right? So there may be a lot of recomputing of certain symbols of F of X, but then that's okay, because now we are not using up the entire space to write down F of X. So F of X is never written down as a whole. We are just looking for, let's say 10th is required, 10th symbol of F of X is required, we just write down the 10th symbol. 15th or 100th symbol is required, we just write down the 100th symbol, and that's it. So we are never writing down the entire f of x at any time. So as and when they are required, they are generated on the fly, and then M continues running. So M just continues running. Let's say it requires a certain symbol, and that symbol is produced and given to it. So we never. So what the problem in this earlier picture was that this output tape for R and input tape for M used to take a lot of space. So now we are avoiding that problem by just rerunning R as and when each symbol is required. So in a way we are sacrificing time by rerunning again and again and again for space. So we are saving on the space, right? Because we are never writing down the f of x entirely in this tape, which is okay because in this model time is never measured. What is measured is the space, right? So now M can complete the computation and M can decide whether f of x is in B or not. And by the properties of the reduction, we have that f of x is in B if and only if x is in A. Hence, we are able to decide A using the decider for B and the reduction from A to B. So we can infer that A reduces to B and B is in L implies that A is in L. So the whole setup here is log space, because M requires log space and the reduction machine also requires log space, but we never write down the output of the reduction machine as a whole. We just write down we just pass on whatever symbols are needed at that point of time on the fly. We end up doing a lot of recomputations, but that's okay because we are saving on the space, right? So that is why this reduction makes sense. So again, this is what we would like to have, and that property is indeed there. So now let us define NL completeness, having seen the reduction, logarithmic space reduction, log space reduction, and the fact that this reduction is sensible. So the NL completeness is very similar to NP completeness, right? Just that we use polynomial log space reduction instead of polynomial time reduction. So a language B is NL complete if first B is in NL, and 2 for all A in NL, A reduces to B in logarithmic space, not polynomial time, logarithmic space. Okay, this is the notation for the reduction, A less than or equal to with a L subscript to denote that it is logarithmic space bounded reduction. Okay, so this is the definition of NL completeness, right? So right. So one language that is NL complete. So just like we had SAT, that was a first language that was NP complete. Here our corresponding language will be path, right? So we already saw path in the previous lecture. And in fact, we even asked, I even mentioned to show that path is in NL, right? Okay. So to show that path is in NL complete, we need to do two things. One is that path is in NL, and for all A in NL, A reduces to path in logarithmic space. So path in NL I already mentioned in the previous lecture, but I'll just give a very brief high level thing. We cannot run BFS or DFS, but however we have the non-determinism, right? So to decide whether S is or T is reachable from S, one way to do it is to just guess one path, just guess a sequence of vertices, right? Let's say S, V1, V2 something, T. Now you just check whether this path takes you to T, is it a valid path? If there is a valid path that takes you from S to T, then you will guess it, and that is enough. If there is no valid path, whatever you guess, it will lead to reject. So that is a high level idea. So the details you can work out. Okay. Now we need to show that for all A in NL, A reduces to path, right, which is the main part of the reduction. So if you have paid attention in the previous lecture, you may guess what is going to come, right? We can construct a configuration graph for A, right? So the A is in NL, right? We can construct a configuration graph for A, right? And in this configuration graph, we can check whether there is a path from the starting configuration to the accepting configuration, right? So C start is what we use to denote the starting configuration, and C accept is the accepting configuration. So I am lying slightly here. C accept is not a unique accepting configuration, right? Because you could be in different, you could have different configurations. So you could have different tape contents, head positions, and so on, right? So there is no unique accepting configurations, but that is what I say here in the next exercise that you can think. If there is a non-deterministic Turing machine with multiple accepting configuration, show that you can get a equivalent non-deterministic Turing machine with a unique accepting configuration, right? So it is very simple. I'll just very briefly highlight the idea. If there are many multiple accepting configurations, what you could do is you could map them. So this is a Q1, Q2, Q3 are all accepting configurations, right? And now I want to have a unique accepting configuration. How can we do that? One way is to sorry. So the point is here is that why do we have the different accepting configurations? Because the tape contents are different and the head positions are different. So we could program the Turing machine to erase the tape content and move the head all the way back to the leftmost position. So if we do that, there will be only and the accept or reject should happen only after that. Again, this is a bit of Turing machine stuff and which you can verify easily. So once you do that, there will be unique accepting configuration. So now in this modified setup, all we need to do is to check whether there is a path from the starting configuration to the accepting configuration. So the starting configuration will be dependent on the input, right? So if for a different input, we'll have a different configuration, obviously, because the tape contents will be different. Tape content at the start contains the input, right? Right. So now we have this configuration graph and we just need to check whether there is a path from this vertex to that vertex, which is exactly the problem that path is, right? Path is just given a graph G, is there a path from S to T, right? So path, maybe I should just mention here. GST. G is a directed graph and has a directed path from S to T. So that is kind of the idea for the reduction. So one point here is that we already saw this in the previous lecture, just repeating. The number of configurations that the machine has, that the machine for NL machine for A has, is 2 power constant times log n, which is polynomial in the input length, right? N power order 1. This is something that we did already. So which means to write down, to represent a polynomially, to represent a configuration, we can have a label of length order log n, right? Because it is just so to represent something we need logarithmically many bits. So log of 2 power order log n is simply order log n. So each configuration has a name, has a name of length order log n. So some maybe C log n or something for some constant. Okay, this is going to be important. So now we have shown that Uh, we have shown that given a machine A in, or given a language A in NL, you take the decider, not NL decider for it, and this gives you the problem of the equivalent path problem. So you have the configuration graph is a graph. Starting vertex is the starting configuration, S is the starting configuration, T is the accepting configuration. But now how does so the equivalence is clear, but how is the reduction performed? So recall that this reduction also must be performed in log space, right? So we have to be careful in doing this because we cannot use more space, right? But then we are dealing with a configuration graph that is of size polynomial, right? It has polynomially many vertices. But it is okay to write down the answer in the work tape, but sorry, not in the work tape, the answer in the output tape, but in the work tape we are constrained for space. So what do? One is that we list down all the configurations, right? So what we are going to do is write down the configuration graph followed by S and T. So S and T are easy to write down in the output tape. So how do we write down the configuration graph? We first list down all the vertices followed by all the edges. So what we do is we list down all the configurations. So this could be done by a counter. So you could just have a counter, and whether it is a valid configuration, this needs to be checked. And as I already said, the length of representing a certain configuration is order log n. So the counter can be of order log n length, right? And at each point of the counter, we check whether it's a valid configuration, right? Because you could have strings that do not make sense. You could have multiple states, right? So a configuration has only one state, right? So you could have no states. So these are all illegal strings that are not that do not correspond to a configuration. If it is a legal configuration, you write it down. Now that after this process, all the configurations would have been written down. Now let us come to the edges in the configuration graph. So what you do is once again you go over all the configurations. So you one by one you go over all the configurations. So that is counter 1. Again, this requires order log n space. Now for each valid configuration generated by counter 1, we generate all the possible successors. So again, it's two nested loops, everything running, both the nested loops running over all the possible configurations. So when 1 is fixed at a configuration, 2 is again checking for all the possible configurations. We check whether it's a valid configuration, and then we check whether it is a successor of the entry in the counter 1. So if it is a valid successor of the entry in counter 1, you list it down as a possible edge of the outgoing edge of the out neighbor of the configuration in counter 1, and so you get an adjacency list of sorts, right? So this 3 counters, O log n counter here, and O log n counter here, and O log n counter here, and maybe a bit of extra space to check whether the configuration is successor, etc. So all that we need is this much for the work tape. So the work tape requires order log n space, right? So and it is deterministic. So the reduction happens in order log n space, and we have a equivalent reduction. So any language in NL, we could convert it to an instance of path using a log space reduction. Again, C start and S is C start and T is C accept. This is easy to note. This is also there in CIPSR. You can have a look. They have a more paragraph writing style, so it may be a bit different, but it will also help you to see different styles of writing, right? So again, this is an example of a case where the reduction is in log space, but the output size is polynomial, right? So now just one exercise which you can try out. show that ANFA is NL complete. So ANFA is a language that you may have seen in theory of computation. NFA stands for non-deterministic finite automaton. Given a description of a non-deterministic finite automaton N and a string W, does N accept W? That is a question. And it turns out that this language is also NL complete. So I'll just give you one hint or maybe two hints. Sorry. So the hint is to recreate the configuration graph as the NFA. So again, one point here, now you can draw analogs of whatever we said for NP completeness. So to show that a language is NL complete, so to show that ANFA is NL complete, it is enough, right? So maybe I'll just say that again. Sorry. Right? It is, so what I want to say here is that to show ANFA is NL complete, we need to show that 1, ANFA is in NL. This is not that difficult. And 2, for all B, sorry, for all, let's say B or maybe C in NL, C reduces to ANFA. So instead of this, what we will do is, since we already have an NL complete language, we will do, which is path, we will just do path reduces to ANFA. This is exactly the kind of thing that we did to show that, let's say, clique is an NP complete, right? So now that we have an NL complete language, we can reduce that NL complete language to whatever languages we desire. Right? Right. So we just need to show path reduces to ANFA. So step 1 is going to be easy. Step 2 is the main thing. So there we recreate the configuration graph, or we recreate not the configuration graph, we recreate the graph. There is no configuration, right? We recreate the graph as the NFA. So the NFA can have the, like, basically the transitions will be defined by the graph. And there are two things, one point, again, I'll just give you one hint. There are two ways to do it as far as I know. One is by a unary language, one is by an empty language, and you could do it either way. You can think about it, right? And another language that I will just mention, that is NL complete. 2SAT is NL complete, right? So 2SAT is when where it's an AND of clauses, and each clause is a OR of 2 literals. So it turns out this is also NL complete. You can think about this. So just to summarize the lecture, we defined the Logspace reductions. We saw why it makes sense. We defined NL completeness. We saw that path is NL complete. So what does it mean to say that path is NL complete? So just maybe a bit more. So given a language A and given a string x is in A, right, we can build an instance of path, say GST, such that, or given a string x rather, not x is in A, x is in A if and only if GST is in path. So the idea is G is a configuration graph of the NL decider for A, S is a starting configuration, and T is the unique accepting configuration. So X is accepted by the machine if and only if there is a path from the starting configuration to the accepting configuration, right? So that is exactly what we check in path. And we also verified that this reduction can be performed in logarithmic space. And then we conclude with a couple of exercises. That's all. Thank you.